Now we change from exponential to logarithmic equations. Notice how we have log base 7 of something equals log base 7 of another something. If we unlog or anti-log each side, we basically get 12 minus t is equal to t plus 6. Now technically we went 7 to the left side equals 7 to the right side and used one of our properties of logs, but if you just want to say, hey, we're setting the arguments equal to each other, that's perfectly fine. Now let's solve for t. I'm going to add t to both sides, subtract 6 off of each side, and that will give me 6 is equal to 2t, therefore t is equal to 3, and that will be our solution set. We can check that it works. When we substitute in 3 on the left, we get the natural log of 9, which is valid. On the right, 3 plus 6 is 9, and we get the log of 9 there. Not the natural log, as I started to say a little bit ago. In this next problem, first thing we probably want to do is divide off that 5 that's in front. Try and get that log by itself. That gives us log base 6 of 7w plus 1 is equal to 2. Now this problem doesn't have a log on the right, and we can't do what we just did in the last problem, but we can get rid of the log by using that property that has us writing this as an exponential equation. 6 squared, which is 36, but we'll write 6 squared here, is equal to 7w plus 1. So that's really a 36 equals 7w plus 1, and we're going to solve this linear equation. Subtracting 1 on each side gives us 35 equals 7w, and w then is equal to 5, and that is our solution set. Now let's take that 5 and substitute it back in the original problem. 35 plus 1 is 36. I just want to make sure that we don't get the log of a negative when we do that. Okay, here we have another problem with a log of q minus 6, which we're trying to solve for. We just have a single log. The base needs to be written in. It's understood to be a common base of a common log of 10, and we can convert that into an exponential equation and have 10 to the 3.5 power is equal to q minus 6. And adding 6 to both sides, we now have q is equal to 10 to the 3.5 power plus 6. And that becomes our solution set if we want an exact value. If we want to substitute that into a calculator and get an approximation, then q would be approximately 3168.2777. Okay, another logarithmic equation, and this time we have logs on both sides, but we've got a 1 there that doesn't have a log on it. So what I'm going to do is bring the log from the right over to the left and get the logs together. That will give us log base 4 of 5x minus 13 minus log base 4 of x minus 2 equals 1. And one of our properties of logarithms is that when we subtract, we can change this into the log of a quotient. So we can write this as log base 4 of 5x minus 13 over x minus 2 equals 1. Now we've got all the logs in one place. Now we can change this to an exponential equation using that property here. We're going to have 4 to the first equals 5x minus 13 over the x minus 2, which is now something we can kind of solve kind of easily. Write this as a 4 over 1 and cross multiply. One diagonal here is going to give us 4x minus 8. The other diagonal will be 1 times the 5x minus 13. Let's get all the x's to one side and the constants to the other side, and this will give us, when we add the 13 to both sides, 5 is equal to x, and that becomes our solution set. Now it could be no solution if it doesn't work when we plug it in, but let's take a look here. In the first argument, we get 5 times 5, 25 minus 13, which is 12, so we get the log of 12. Here we get 5 minus 2, which is 3. It's not a negative number there, so I think we're pretty good on that. And 5 is going to be the answer we're going to go with.